For a long, long time, we've thought about aging as this inevitable decay, right? Like a machine just wearing out. But what if that whole picture is wrong? Today, we're going to dig into a really different idea that's changing everything. An idea that frames aging not as physical damage, but as a loss of information.
This is the big question. Let's just park the idea of rust and decay for a minute and think more like software corruption. What if aging is actually a correctable bug in our biological programming? This one shift in thinking is already transforming how science approaches health and how long we can live.
Okay, so to really get where we're going, we first have to understand the story we've been telling ourselves about getting old, and more importantly, why that story just isn't cutting it anymore.
The scale of the problem is just massive. Aging isn't just one thing. It's the #1 risk factor for about 90% of all the major diseases we face. Heart disease, cancer, dementia, you name it. So what this really means is that tackling aging itself could be the single most powerful thing we could do in medicine.
For decades, the main theory was all about wear and tear. The idea that our bodies just accumulate damage from things like free radicals, and eventually we break down. And, it makes sense on the surface. But here's the problem. When scientists tried to fix it, like by giving people massive doses of antioxidant supplements, it consistently failed to make people live longer. So it became pretty clear that damage is only a small part of the story.
And that brings us to this new and I think much more powerful idea, the information theory of aging. It suggests the problem isn't so much with our biological hardware, but with the cellular software that's supposed to be running the show.
This is the core idea in a nutshell, and the crucial part is this. It suggests our bodies don't actually forget how to be young. The original instructions are still there, but the way our cells read those instructions gets scrambled over time.
So how does this information actually get lost? To get our heads around this, we need to look at two different but related systems inside every one of our cells. There's a really simple but powerful analogy that makes this all click.
First up, you've got your DNA. You can think of this as your body's hard drive. It's digital information. It's the blueprint with all the instructions to build every single part of you. And for the most part, this digital code stays almost perfectly intact your entire life.
But which parts of that blueprint get read and when? That's the job of the epigenome. So if the DNA is the hard drive, the epigenome is the software. It's the program that's reading the data. It's what tells a skin cell to act like a skin cell and not a brain cell, even though they both have the exact same DNA hard drive.
Let's really nail this down with that analogy. Just picture your DNA as a brand new CD with a perfectly recorded song on it. The ones and zeros, the digital data for that song, are flawless.
When we're young, that CD is pristine. The player reads it perfectly and you get a beautiful, clean song. That's a healthy young cell. But over time, the CD gets scratched. These scratches, which scientists call epigenetic noise, are caused by all sorts of things: DNA damage, inflammation, just life happening. Now the digital music is still perfect, but the scratches confuse the CD player. The song starts to skip, it gets distorted. That is aging. The cell starts to misread its own instructions, it forgets what it's supposed to be, and it starts to malfunction. And that leads to the diseases we all associate with getting older.
Now what's so cool about this is that it isn't just a clever analogy. Scientists now have the tools to actually go in and measure these scratches. We can literally quantify this loss of information.
And this brings us to a really important distinction. There's your chronological age. That's just how many birthdays you've had. But then there's your biological age, which is the true functional age of your cellular software. It's a measure of how much epigenetic noise you've built up, and it's a way better predictor of your actual health.
So how do we actually read it? Well, scientists use something called an epigenetic clock. These clocks work by analyzing the patterns of these tiny chemical tags on your DNA called methylation. By reading millions of these little tags, they can calculate your biological age with incredible accuracy. It's essentially a direct readout of how scratched up your CD is.
Now, the good news here is our bodies aren't just helpless. We have these ancient survival circuits that act like a cellular defense force. Pathways with names like sirtuins, mTOR, and AMPK. They respond to good stresses like exercise or fasting, and they help clear out junk and guide the epigenome, basically helping to quiet down some of that noise. You can think of them as the body's own software repair crew.
And this is where the story takes a really incredible turn. Because if aging is just information loss, could we restore that information? Could we actually polish the scratches off the CD?
The pace of discovery here is just breathtaking. Look at this. In 2013, we got the first reliable epigenetic clocks. Just a few years after that, Shinya Yamanaka won the Nobel Prize for figuring out how to reprogram adult cells all the way back to their original youthful state. And by 2020, this led to some absolutely groundbreaking experiments.
Okay, so let's get specific. Researchers took old mice that had damaged optic nerves. It's sort of like glaucoma in humans. Then, they used a safe little cocktail of just 3 of those Yamanaka factors to essentially reboot the software in those nerve cells. The result was just, well, it was astonishing. The damaged nerves actually started to regenerate, which was something we thought was impossible in adult mammals.
And they didn't just look better, they were measured. Using those epigenetic clocks, scientists found that the biological age of those neurons had been cut by about half. The cells weren't just working better, they were quantifiably, measurably younger. They had, in effect, polished the scratches right off the CD.
So this leaves us with a pretty profound question, doesn't it? We are literally moving from a world where we can only watch aging happen to one where we can actually read its code. The next logical step, and really the great challenge of our time, is figuring out how to rewrite it. The story of aging isn't just about damage anymore, it's about information. And the beautiful thing about information is that it can be restored.